Rates of chemical reactions. The collision theory is used to predict and explain how reactions occur and what causes the rates of reaction to change. The collision theory is based on the assumption that all reactions need to have a collision between the reacting species, and these collisions need to happen within the required activation energy, and they need to form an activated complex. Activation energy is the minimal amount of energy needed of the particles to produce the reaction. The activated complex is a highly energetic compound formed as a temporary state between the reactants and the products. It only forms when a successful collision occurs, but as it can become the products or revert back into the reactants, not all collisions that produce an activated complex results in a successful reaction. The collision theory also explains why different factors change the rate of reaction. These factors include energy, concentration, surface area, catalysts, agitation, state of matter, and light. Energy affects the rate of reaction because as energy is added to the reactants, generally through heat, the particles' oscillations increase in rate and magnitude. This increases the chance that the particles will collide with the right orientation to react and with enough energy to break and reform bonds into the product. An example of how energy affects the rate of reaction is in the reaction between thiosulfate and hydrochloric acid, which can be seen in this video. In the reaction, it was shown that as the temperature of the reactants increased, so did the rate of the reaction. This did so by a large amount. A 45 degrees Celsius rise in temperature of the reactants caused the time to drop by 4.19 minutes. Therefore, these results support the theory that as you increase the energy of the reactants, the reaction rate increases. Molar concentration refers to the amount of particles of a solute in a given volume. Pressure is similar to this, except it involves gases instead of liquids. Increasing the concentration affects the rate, as the solute with a higher concentration will have more particles in the same space, which increases the number of collisions with the other reactant. Two experiments were performed to show the relationship between concentration and reaction rate. The first experiment was between magnesium and differing molar concentrations of hydrochloric acid, and the results showed that the magnesium placed into 2 moles of HCl took 1 minute and 54.2 seconds to react completely, while magnesium placed into 0.5 moles of HCl was still ongoing after 14 minutes. The other reaction was a Koch reaction involving different dilute versions of potassium iodide, reacting with hydrogen sulfide. The results showed that there was an 18.7 seconds gap between the quickest reaction, which had the lowest dilution factor, and the slowest reaction, which had the highest dilution factor. Thus, these results support the theory that concentration affects the rate of reaction. Increasing the surface area of the reactants increases the reaction rate, as more particles are exposed and are available to react. Powdered form of the reactants usually react faster compared to solid lumps because, as seen in this diagram, solid lumps allows only the outside particles to collide and react, while powdered forms allow particles which were once trapped behind the outside layer to be exposed so they are able to react. The experiment performed to test this theory was the reaction between marble chips in lumps and powdered form in hydrochloric acid. This video of the reaction shows that the powdered form of the marble chips, which had the greatest surface area, produced a much faster reaction compared to the marble chips in lumps, therefore supporting that surface area affects reaction rates. Adding a catalyst to a reaction increases the rate as a catalyst lowers the activation energy required to produce a reaction. As seen on the Maxwell and Boltzmann distribution graph, this means more particles have the energy required to react, which increases the frequency of successful collisions between the reactants. This theory was tested by adding a catalyst, which was copper sulfate, to a zinc and hydrochloric reaction and observing and recording the results. Even though the results showed that the reactions finished at the exact same time, which is a surprising result, the reaction with copper sulfate started a lot faster than the one without, which can be seen in this video. Agitation affects the rate of reaction by removing the build-up of products around the reactants, which allows more collisions between the reactants to occur. The state of matter affects the rate as well. Aqueous solutions of the reactants usually react faster than when in solid form. This is because the reactants in aqueous solutions usually have a larger surface area and are already split into their ions. Many bonds do not need to break and reform to produce the reaction, which lowers the activation energy. This was tested in the lead nitrate and sodium iodide reaction, as the reactions were compared when they were in solid form with no agitation, with agitation, and when they were in aqueous solutions. And the video helps show that the reactions in aqueous solution had the fastest reaction, while the reactions in solid form with no agitation was the slowest. Therefore, these results support the statement that agitation in state of matter affects the rate of reaction. Light reactions are photolysis reactions. These are reactions where compounds are broken down by photons. These reactions involve free radicals, which are molecules or atoms which have one unbonded valence electron. When a light photon collides with a molecule, they have enough energy to break the bonds, forming a free radical molecule. These particles are highly energetic and reactive. Light doesn't affect the rate, but is the reason some reactions occur. This can be seen in the decomposition reaction of silver bromide. When light photons collide with silver bromide, they transfer enough energy to allow the molecule to overcome the intramolecular forces, thus causing the molecule to split into its ions. This is shown through observing the difference between silver bromide, which has been exposed to light, which has undergone a chemical reaction, and one that hasn't been exposed to light when no chemical reaction occurred. So these results support the statement that light causes reactions to occur. In conclusion, the collision theory is used to explain how a reaction occurs and why factors such as energy, concentration, surface area, catalyst, agitation, state of matter, and light affect the rate of reaction.